This is the November 2019 Timezone 0 Physics HL Paper 1 for IB Physics video walkthrough. So let's begin with question 1. In question 1, we're presented with 4 options and we're asked which quantity has the fundamental SI unit of kg meters to the power of -1 second to the -2. So the first step is let's just write down the formulas for these 4 options. So we know energy is equivalent to work, which is force times distance. Force is equal to mass times acceleration. Momentum is mass times velocity. And pressure is the force over area. So if we look at all of these 4 terms, we can already make a good estimate that the answer would be D. This is because we have a area term here getting divided, which I suspect would lead to this meters being to the power of -1. So let's just quickly walk through. Let's find out force first. So force is mass times acceleration. And acceleration we know is the change in velocity per second. So it's just kg meters second to the power of -2. So this is the unit for force. So we already know it's not option B. Now with option A, it's force times distance. So this multiplied by distance would add a m, which would give us m2. But that is not what we have here, so it's not option A. And we can already deduce that if we multiply by ms minus 1, we get a m2 and a -3, which means it's not option C, which means the answer for question 1 is D. But let's just quickly walk through the solution. So we have force, which is equal to kg meters to the power of -2. Now if we divide this by area to get pressure, it will be m minus 2. And when you're dividing units, it's kind of like dividing variables in algebra. So you get kg m minus 1 s minus 2. And that's our answer. So now moving on to question 2. We are presented with an object that is initially at rest. And one of force is constant and the second force is in the opposite direction and proportional to the velocity of the object. So if you read this scenario, it does sound quite familiar. What we have here is actually an object falling down. So we have the constant force, which is we can imagine as weight, and this is air resistance or drag. And this is, we can put this as air resistance or air drag because this is proportional to the velocity of the object, and we know the object is initially at rest. So this means that eventually the object will start off at 0 and will reach a maximum speed where the velocity of this object is fast enough that the varying force is the same amount, same magnitude as the constant force. And this means when both forces are equal and opposite direction, the net force is equal to 0. And this means there will be no acceleration. This means for this one, we have an option C is our answer. And this is because velocity increases from 0 to a maximum. And at the maximum, this is when the total force sums up to 0. Now let's move on to part 3. We have a ball that falls from rest in the absence of air resistance. And the position of the center of the ball is determined at 1 second intervals from the instant at which it is released. What are the distance in meters traveled by the center of the ball during each second? Now this is a bit of a trick question because the values presented here is how much the ball travels in each second, not the actual total total distance traveled. So you just can't take Suvat equations and put the 4 seconds and expect it to be 80. So option C is actually a trick question, and I'll walk you through the maths. So let's just take G to be equal 10. And this is because you can't actually have a calculator in paper 1. So I would advise everyone to take the gravitational constant as 10. Now we're looking for distance here. So for the S term, we have the initial velocity, which is 0. We have time, which is a total of 4 seconds. And we have acceleration to be 10. Now let's just look through our Suvite equations in the subtopic 2.1 in our data booklet. And we can use this equation. So this term cancels to be 0 because initial velocity u is 0. So 0 times 4 is equal to 0. So we have half multiplied by 10 multiplied by total time is 4 seconds, so 16, which gives us s equals 80 meters. So this is after 4 seconds. So you might be tempted to think it's c because you see that 80 here is 4 on the 4th second, but that is false. This is because this is the total distance traveled in 4 seconds. And what we have here is the distance traveled in each second. So to find out the answer, what we have to do is we actually have to add up all of these and find which one equals to 80 meters. So if we just add this up, quickly add it up, is 50 meters for option A, so it's not option A. For option B, we have 20 plus 45 plus 35 is 80 meters. So we know it's option B. But let's just go through. So we know C, it's definitely 80 and above, and for D, it's definitely 80 and above. So the answer for this would be option B. Question 4. So in question 4, it's basically a projectile motion question, and we are asked, out of these 3 quantities, which quantity do we need to know in order to determine the horizontal distance from the point of projection to the point at which the object hits the ground? So obviously, let's look at each one and see which one is needed. So for the first one, we obviously need the initial velocity of the object, especially the horizontal component. Now for number 2, we also need that because the initial angle determines how much of this velocity will be translated into the horizontal component or the vertical component. So for example, at a greater angle, more of the velocity v will be translated into the vertical component and less into the horizontal component. Whereas compared it to, let's just say, a smaller angle, more of the velocity will be translated into the horizontal component and less into the vertical component. So that's why the initial angle matters. And now, lastly, for the height of the cliff, this one matters because if you can imagine, a higher cliff would mean more time in the air. And when there's more time in the air, that means there's more time for the ball to travel. And given that horizontal velocity is constant throughout this entire projectile motion, the higher the cliff, the more distance it will travel. Therefore, we need all 3 components to determine the horizontal distance. And therefore, for question 4, we would select option D. Now, in question 5, we're presented with an acceleration time graph, and we are asked to determine the change in velocity of the object from time equals 0 to time equals 6 seconds. So we know that acceleration is basically change in velocity over time. Now, we're presented with acceleration here and time here. That means if we find the area, it's basically acceleration times time, which gives us what we're looking for, velocity. Hence, we just have to find the area under the graph. So what I normally like to do is to divide the graph into simple shapes. So here I've divided it into a rectangle and a triangle. So the area of the rectangle is just 6 seconds multiplied by 1, which gives us 6 meters per second. Now the triangle is 4 seconds and 2 meters seconds to the power minus 2 tall. But because it's a triangle, it's just 2 times 4 times half. And that gives us 4 meters per second. Now we're finding the total area, so we add them up together. That gives us 10 meters per second. So that's for question 5, option C. Now, moving on to question 6, we have a nuclear particle that has an energy of 10 to the power of 8 eV. So eV stands for an electron volt, and this is actually the energy that is exactly the same as an elementary charge of an electron. So you can find the how much an elementary charge is in your data booklet. Just navigate to the fundamental constant table. So we can find out that an elementary charge is actually equal to 1.6 times 10 to the power of 19 coulombs. Hence, an electron volt is the exact same thing but in joules. And we're given that it is 10 to the power of 8. So that means 10 to the power of 8 eV is just 10 to the power of minus 19 times 10 to the power of 8. So we just add the 2, which is 10 to the power of minus 11 joules. Next, we are asked at what speed of this grain of sand must have for the kinetic energy to equal the energy of the nuclear particle. So this is the energy of the nuclear particle, and this is the mass of a grain of sand. So Ke is half mv squared. So we know the mass is 3.2 times 10. Now to figure this out, we know the SI unit for mass is kilograms. So if we're going to express this in grams, this is times 10 to the power of minus 3. And to further go to milligrams, it's another 10 times to the power of minus 3. Now this means that this is actually 10 to the power of minus 6, but because I moved the decimal place forward by 1 to be 3.2, we can express it as 10 to the power of minus 5 multiplied by v squared. And that gives us 1.6 times 10 to the power of minus 5 times v squared. So this means that we are missing, or to make these two equivalent, we are missing a times 10 to the power of minus 6. So that means v squared must equal to 10 to the power of minus 6, which means v is just 10 to the power of minus 3. Now, if we look at option A, this actually matches our criteria, and that is our answer, because this is meters per second and this is millimeters per second. So that is in velocity. So option A is basically 1 times 10 to the power of minus 3, which is just equivalent to 10 to the power of minus 3, which is what we're looking for. So option A is the answer for question 6. Now moving on to question 7, we are asked about the tension in a horizontal spring is directly proportional to the extension of the spring. The energy stored in the spring at extension x is E. What is the work done by the spring when its extension changes from x to x divided by 4? So let's just find a way to express what E is in this case. So if you navigate to your formula booklet, you can see in subtopic 2.3 that we have a formula for expressing the energy stored in a spring, which is energy is equal to half spring constant times the change or displacement in the spring extension. So in this case, we'll just leave it as x. So we know that this is the initial energy it has. However, in this question, the extension changes to x divided by 4. So that means the new energy, which I'll denote as x1, is equal to this. Now we have to make sure that the extension becomes x divided by 4, and we have to make sure that we squared the entire thing. So that will equal to be half k x squared divided by 16. Now this is the energy stored in the spring at this instant. And now we know that this is the initial energy. So I'm just going to write that down. Initial when it's x. And now this is the final when it's x over 4. So what this means is that we're actually looking for the difference. The difference between these two energies is the work done by the spring, because the energy had to go somewhere. So initially we have half kx squared and now we only have half kx squared over 16. So we're looking for the difference here. And what you can do is you can just minus these two terms. And you may notice that what determines the energy here in this case is actually this component right here, 15, 16. So what we have to do is we can actually re-express this entire expression in terms of E. It's basically E minus 1 over 16 E. Now we can do this because half k x squared over 16 is equivalent to half kx squared times 1 over 16, and this component here is equal to E. Hence we can get it like this, which means our answer is 15 divided by 16 times E, which is option D. Now moving on to question 8, we have a mass m of water at temperature 290 Kelvin, and we're given some information about the specific heat capacity of water is C. So we're also given that ice at its melting point is added to the water to reduce the water temperature to its freezing point. And we're given the latent heat of fusion for ice is L. And we're asked about what is the minimum mass of ice needed. So what we have here is actually a thermal diffusion question. We know that the freezing point of water is 0 degrees Celsius or 273 Kelvin. So this means that we have to change the water from a temperature of 290 to 273, which is a temperature difference of 17. So we can just do 290 minus 273 and 17. That means we have to change the temperature of the water by 17 degrees. So we know that the energy required to do this is just m, which is the mass of the water. I'm going to denote this with mw. So mass of the water multiplied by the specific heat capacity of water and the change in temperature, so 17. So where are we going to get this energy, or where's this energy going to go? So this is going to go into the latent heat fusion of ice. So the energy from the water, some of this heat energy is going to go into melting the ice. So let's form our equation here. We have a mass of ice and we're given the latent fusion. So now we've formed the equation. The energy going into the ice is equal to the mass of the ice multiplied by the latent heat of fusion for ice. Now these two energies have to equal because the energy has to go somewhere in this system. So we have mass ice is equal to mass of the water times C times 17. We are asked to find the minimum mass of ice, so we're looking for Mi. So that gives us 17 times mass of the water times the specific heat capacity of water C divided by L. And that gives our answer to be option A. So now let's move on to question 9. So I've gone here and written some statements about what makes an ideal gas. So statement 1 is that there are no intermolecular forces in ideal gases. This means that the particles of the gas particles of an ideal gas, they don't really have a lot of forces in between each other. Now for number 2 of an ideal gas is that volume occupied by the molecules is nothing compared to the total volume occupied by the gas. So this means that the molecules within the actual gas occupies a very, very small amount, which means that there's very low density. That means we can get rid of option A and option C. Now, in order to reduce IMF, we can imagine a container here. If there's very little IMF, that means there's very little forces in between each particle, which in turn means there's very little forces that will cause the particle to bounce off the walls. And this bouncing is actually what causes the pressure. So we actually want low pressure and low density for a real gas to approximate an ideal gas, which means our option is D. Now, moving on to question 10, it says that two flasks P and Q contain an ideal gas that are connected with a tube of little volume compared of that to the flask. The volume of P is twice the volume of Q. We know that P is held at a temperature of 200 Kelvin and Q is held at a temperature of 400 Kelvin. And we're asked to represent the mass of the gas in P over the mass of the gas in Q as a ratio. So right away, I know that this is a topic 3 question. And what we can do is we can use the formula PV equals nRT. Now I know we can use this formula because we're given the volume, we're given the temperature, and we know that N and R are constants. So N is the amount of gas in moles, and R is a 8.31 constant. So we also know that pressure in this case will be constant because they are connected through a tube. Now this means that the pressure within both of these would be shared. So what we can do is we can actually rearrange this formula to be in terms of P. So let's start off to represent flask P. So the pressure in flask P is nRT. We know that this is at 200 and the volume is twice as large. So in this kind of questions, you always want to set the smaller one as V or as a constant and the larger one as some sort of multiplication of the smaller one. So because the volume of P is twice as large as the volume of Q, if Q is equal to V, P must equal to 2V. So this is our pressure equation for flask P, and now this is for flask Q. So we have nRT, which is 400 over V. So what we have here is because we know that both the pressures must equal, we can equate both equations. So N, I'm going to add a P here, so NP, so we know which flask we're talking about, over 2V is equal to N, this is Q, R, sorry, missed out an R here, times 400 over V. So we can actually simplify this. These cancel out to be NP 100 R over V, and this gives us NQ R 400 over V. So we can actually get rid of the R's and the V because they appear both sides on our equation. And now we want to get the mass of the gas in P and mass of the gas in Q. So P on top and Q underneath. So although this is in moles, we know that moles of gas directly equate into mass. Moles is just like another unit to measure an amount of gas. And because we're working in terms of ratios, if we find it in moles, we can assume that it equals, the ratio will still hold true even though we're talking about mass in the question. So what we can do is we can divide both sides by NQ, which gets rid of NQ here, and divide both sides by 100. So we get 400 divided by 100, and that equals 4. So that means for question 10, our answer is C. So in question 11, we're presented with a transverse traveling wave, and we have a distance displacement diagram shown here. We're given information about the frequency of the wave to be 25 kilohertz and the speed of the wave to be 100 meters per second. So let's go through option A first. So option A is the particles at X and Y are in phase. Now we know this is false because to be in phase they have to be in the exact same location. So this particle here and X would be in phase, for example. So option A is not an option. Option B, the velocity of the particle at X is at a maximum. That is false because at X the velocity is actually at 0 because the particle has just gone up and now it's going down. So velocity is just at 0. So option B is false. Now, the horizontal distance between x and z is 3 meters. So to figure this out, let's find out the wavelength of this wave. So we know the wave speed is 100, and we know wavelength multiplied by frequency would get us the wave speed. So 100 is equal to 25 times wavelength, and wavelength is equal to 4. So one wavelength is actually from particle x, right here, all the way to here. So we know that this is 4 meters. And what they've done here is that they divided it, let's add in another node here, into 4 segments. So this would be the first one, second one, the third one, and the fourth. And we know that these all have to equal to 1 meter in horizontal distance. So we have 1 meter, 1 meter, and 1 meter. This means that the distance between x here and z would be 3 meters, which means that option C is the answer. And we definitely know that option D is false. So let's move on to question 12. So question 12 is another wave question. We are presented with a displacement time graph now, showing the displacement with time of a particle in a traveling wave, and we're asked to deduce the frequency and the amplitude. So first things first is let's find out the amplitude, because this is the easiest thing to do. The amplitude is basically the distance from the top all the way to the midsection of the wave, and in this case it's just 2. So we can eliminate option B and D. Now to find the frequency, we just have to find the time it takes for the particle to go back to where it started. So we can see that it started at the top here at a displacement maximum of +2 at 0 seconds here, and it took them 20 times 10 to the power minus 6 seconds to reach here. We know that frequency is equal to 1 over time period. This means that if we take the frequency here, 1 over 20 times 10 to the power minus 6, this would give us frequency of, so this would be divided by 10 to the power minus 6 would give us 1, 2, 3, 4, 5, 6 over 20. So we take it like this, 100,000 hertz divided by that would give us 50,000 hertz, or 50 kilohertz. That means our answer here for question 12 is C. So let's move on to question 13. So in question 13, what we have here is we have two polarizing filters, X and Y, and they're arranged so that the light emerging from Y has a maximum intensity. So to do this question, we just have to head to our formula booklet to find the formula for intensity, because we want the light here to have maximum intensity. So what we're changing between all of this scenario is the angle of Y. And we know intensity is given by this equation, where the intensity outwards is equal to the intensity initially multiplied by cos squared theta, where theta is the angle. And now in the MCQ question, we're asked what are the 3 successive values of theta, or the angle, for which the final transmitted intensity is at a maximum. So what we can imagine is a cosine graph. But what I actually like to draw out is the unit circle. So we know that cosine is the distance, the horizontal distance in this circle. So we know it starts off at 1 when theta equals 0. I'm just going to write, so this will be theta here. And it goes to 0 here at 90, goes back to 0 at 180. It goes back to -1 here, 0 here, 1 here. So it kind of looks like this. And this would be 180. This would be 0. And it goes back to 0 here, and it comes back to 1 at 360 degrees. So what this means that it starts off initially at 0, and it goes back to 1, a value of 1. And because it's squared, the -1 actually becomes +1. So this means that we're looking for values of angles that are some sort of multiple of 180. So if we look at our options, only option C satisfies this condition, especially if they say successive. As you can see, we're adding 180 here and we're adding another 180 there. So for question 13, the answer is C. So this is question 14. So in question 14, we have a pipe that has a length of 0.6 meters and is filled with gas and closed at one end. And then we are given that the speed of sound in the gas is 300 meters per second. So we know that this is a standing harmonic question. So I've gone and drawn the two different diagrams here for the first and second harmonic that could be formed in the tube. So we know in the first harmonic, as you can see by the diagram, that this is actually 1/4 of a wavelength. So I've gone and highlighted this standing wave in the full wave diagram, and you can see it's 1/4 of a wavelength, with a wavelength being this long. So now I've drawn the second harmonic, and as you can see, this is actually 3/4 of a wavelength. So you may ask, how did I come up with this diagram? So we know that if it is a closed pipe, this has to be a closed node, and this would be an open node. So as you can see, it is open. And for the second one, we know that we just add an extra node inside, and it's kind of the same thing. And you can just keep doing this for the third or fourth harmonic. Alternatively, you can just memorize these formulas and apply them in the question. So let's just start applying them. Let's find out the wavelength for the first harmonic, which I will denote as wavelength 1 here, and it works out to be 2.4. So we know that the speed of a wave is equal to the wavelength multiplied by frequency. So we can just use it to find the frequency. So 300 divided by 2.4 to get frequency, and that is 125 Hertz. So we know the option is either A or B. And now for the next one, we have wavelength 2 is equal to 3/4 or 0.6. So move the 4 over, 2.4, and that means move the 3 over, which is 2.4 divided by 3, which is 0.8. So 300 divided by 0.8 is equal to the frequency. Now you won't get a calculator in the exam, but you can work this out by hand, and that will get you 375. So the option for question 14 is B. Now moving on to question 15. So in question 15, we have a negatively charged particle in a uniform gravitational field, and it's positioned midway between two charged conducting plates. So if I actually draw the forces out here, we know that because this is a negative charge, opposite charges attract. So we have a force going upwards, and we have a gravitational field that is pulling the particle downwards. So now the question asks, what change would cause the particle to accelerate downwards relatively to the plates? So we want a change that would cause the particle to accelerate downwards. So the answer for this is actually option A, and this is because if we reduce the charge of the particle, which means that the electric attraction, the electric force between this negative charge and the positive charge would reduce, because the negative charge is charged less negative, if that makes sense. So I'm just gonna find the formula for you. Just navigate to section 5 of your data booklet. We can see that force is equal to K, Q1, Q2, and R squared. So we know that if we reduce the charge of one of them, it would reduce the force. Hence, this gravitational stays constant. This gravitational field from the force from the gravitational field stays constant. Hence, we have a larger net force downwards, which causes the particle to accelerate downwards. So the answer is A. Now moving on to question 16, we are asked to find the magnitude of P for the reading of the ammeter to be 0. So we want current here to be 0. This entire circuit, if we ignore this section, is actually just a voltage divider. So what we have is we have a 24 volt battery, 2 resistors, 9 and 3 ohms. But I'm just going to simplify them to find the current going out of the battery. So to do that, we just add up the resistors to be 12 ohms, and using the voltage, current, and resistance formula, we get a resistance of current of 2. So I equals to 2 amps is the current. Next, we can find the voltage at this resistor. So how much voltage actually gets expelled. Now we can use this because we know V equals IR. So V in this case is 9 times 2, which is 18, and V here, because we know 24 minus 18 is 6, but just double check, 3 times 2 is also 6, is equal to 6. That means if we want the ammeter to be 0, that means no current flows through here. We should have a power supply here, an EMF of 6 volts too, because this means that no current will be flowing here because these two equal each other and cancel out. So that's for question 16. The answer is B. Now moving on to question 17. In question 17, we are asked that we have a wire with an electric field I is placed in a magnetic field of strength B and experience a magnetic force F. What is the direction of F? So for this kind of question, we should already know by heart that the answer should be D, that the force will be 90 degrees to the plane containing I and B. Now moving on to question 18. Question 18 is a bit of a hard question. They present us with a diagram like this and ask us to find what is tan theta. But for some reason, the question doesn't really explain or give any hint on how to find tan theta. So what tan or tangent actually means is that the opposite and adjacent of a right angle. So I'm just going to quickly draw a right angle diagram here. Assume that this is theta. The opposite would be this and adjacent would be this, these sides. And the tangent is simply just the opposite side divided by the adjacent side. And in this physics question, we're not trying to find the actual length or how long the side is, we're actually trying to find the force. So what I've done is that they've given this diagram and I basically transformed it by moving this line to here. And by doing that, I can also move the radius up here. And this forms the right angle here and moves the theta over here. Now, I know that theta is equal to this and this because over here, as you can see, we have a right angle. And that is the same situation over here. So I hope that makes sense for you, and that's how we came up with this diagram. Now, as I said, we're moving tan as a force, and the forces on this ball is tension here and weight, which is from the gravitational force. So this means that the adjacent is actually equivalent to this here, this line, and the opposite is this. Now the vertical line we know is mg. Next, we know that tension actually provides both of these components. And what force goes towards the center here? It's actually the centripetal force, which causes the ball to move in a circular motion. Or rather, the circular motion causes the centripetal force. And the formula for centripetal force, which you can find in your data booklet in subsection topic 6, is force is equal to mass times angular velocity times the radius. So if we put that in, and we know that this is equal to tan theta, the masses cancel out, which leaves us with an answer of W squared times R times divided by G. which gives us an answer of option A. So this is question 19. Question 19, we are presented with nuclide X that decays by two different routes. So let's go through each option that we have to choose that is correct. So option A is Q and S are different isotopes of the same element. Option B, the mass of numbers X and R are the same. Option C, the atomic numbers of P and R are the same. And option D, X and R are the different isotopes of the same element. So right away, I know the answer is option B. Now I know this because X and R are right here. And the difference between X and R is that X has undergone beta minus decay to form R. And beta minus decay does not impact mass. Now this is because beta minus decay is just a electron that is being emitted outwards. And an electron has zero mass. Hence the mass does not change between X and R. And that's why the answer is B for question 19. Moving on to question 20, we have a proton, an electron, and an alpha particle. And we have to deduce which row is correct in this table. So smallest charge to mass ratio. So what a charge to mass ratio, it can basically be expressed as charge over mass. And that is our ratio. So a bigger charge over a bigger mass. So that would give us we want a very small number here. So let's just go through each one. So a proton would approximately gives us a ratio of 1. A alpha particle would have a charge of 2 divided by 4 because the mass is larger. He has 2 neutrons and 2 protons. So that would give us half. And an electron, we already know, would be very big. Because if you have a very small number getting divided by the smallest number, it should become a very big number. So I'm just going to leave it as that. So we already know it should be A. Now for question 21, the answer is B. So we know that gamma radiation affects a photographic plate, and the rest does not really apply. You can use process of elimination for these kind of questions. Now moving on to question 22. Now question 22 is a bit of a weird question as well. Let's go through each one. So applied to all accelerations, that is false. It has to be uniform. Cannot be proven. It can be proven through maths. And it does relate force to other quantities in mechanics. No, actually it doesn't. And that leaves D. And it makes sense that option D would be the answer too. Now for question 23, this is a topic 8 question. We have to deduce the difference between specific energy and energy density. So we should know this by heart, that specific energy is always by the mass and density is by per volume. Another way to remember this is you also have the specific latent heat, for example, and that's also based on mass. So the option B is the correct answer for question 23. So next is also a topic 8 question. What is the function of the moderator in a thermonuclear fission reactor? So we know that the moderator is actually to decrease the kinetic energy of the neutrons emitted from fission reactions to kind of slow it down so that the reaction doesn't go out of hand. And that matches up with option A. So option A is the answer for question 24. Next, question 25 is another topic 8 question. It says, what is meant by the statement that the average albedo of the moon is 0.1? So I've gone and included the formula here for albedo. Albedo is basically just a ratio between the reflected light and the total incidented light on an object. So in this case, we're talking about the moon. So looking at the question, we already know that the answer should be C, because this is 10% of the radiated incident on the moon is reflected by its surface. And this is reflected because this is equal to just 1 over 10 to be 0.1, or it could also be this, which is 10%. and that's why, as you can see, reflected over incidented, and that's why for question 25 our answer is C. So for question 26, an object undergoes simple harmonic motion of amplitude xo. When the displacement of the object is xo divided by 3, the speed of the object is v. And we are asked to find the speed when the displacement is back to xo. So what we can do is we can apply this formula that we have in our data booklet, section 9.1, simple harmonic motion, which is the speed is equal to the angular velocity square root initial square. So what we have here is that if we put this in, this is the current displacement, and this will be the amplitude. So if we put this in, as you can see, we actually get v equals 0, because these two are the same, hence they equal 0. So our answer for question 26 is A. Now moving on to question 27. So question 27 is a single slit diffraction question. Initially you have a light with frequency 500 terahertz is incidented on a single slit, and they tell you that the first diffraction forms at an angle of 2.4 times 10 to the power of minus 3 radians. And now they change the light to 750 terahertz, and they're asking you to find the diffraction. So the thing is that in the formula, which you can find in subtopic 9.2 for single slit diffraction, you have the angle in radians, which is equal to wavelength times the single slit. So in this question, you have no information about the wavelength or the single slit. But what we can do is we can actually compare the difference between changing 500 to 750 frequency and how that affects the angle. So we can do that by first noticing that for both instances, the light is the same. So the speed of the light would remain the same. Hence, speed of light is equal to frequency multiplied by wavelength, and which means that wavelength is equal to the speed of light divided by frequency. Now we can put that in here, divided by b, which is equal to CFB. So when the light is at 500, we have an angle of 2.4 times 10 to the power of minus 3 radians when the frequency is 500. Now these two stay constant even if we change the light to 750. So by changing the light to 750, what is happening is that we're taking this term and we're actually multiplying it by 1.5. So when we multiply that by 1.5, how does that affect the term here, the radians? So I'm just going to copy this over. And we multiply the bottom term, the frequency, by 1.5. So what that actually does is that we actually have to take our answer here and divide by 1.5, because we're adding this term in by increasing the frequency to 750. And what that is doing is we're getting 2.4 divided by 1.5, which is equal to 1.6 times 10 to the power of minus 3 radians. So that means for question 27, our answer is A. Okay, now moving on to question 28. This is a diffraction grating question. So we shall use this formula that we can find in subtopic 9.3, which is our diffraction grating formula. So n in this case is telling us the order of this maxima, and we're looking for a second order. So 2 wavelength is equal to d. D is the diffraction spacing. And now we just have to rearrange in terms of sign. And the wavelengths cancel out. And now we can see that we're looking for the the angle, so we get the inverse of sine 2 over 3. However, this is from the center, so there are going to be some maximas here. And what we have found is we actually found from the center, so the angle between these two here. But the question is asking the angle between the two second order. So let me just highlight the word 2. That means we have to multiply it by 2 to find the distance between these two, the angle between these two second order maxima. So we take our answer and divide by 2, which gives us 2 sine minus 1, inverse 2 sine, and to the power of 3, which is the answer C. I'm not too sure why it's blurred there. Alright, now moving on to question 29. In question 29, we have sea waves moving towards a beach at a constant speed of 2 meters per second. And we know they arrive at the beach at 0.10 hertz. And we have a girl on a surfboard that is parallel to the wavefront. So when it's parallel to the wavefront, that basically means that the waves are moving this way, and they're either pushing the girl this way, or they're pushing the girl towards the beach, essentially. And she observes the waveboard crosses the wavefront with a frequency of 0.4 hertz. So by comparing the frequencies, we know that the waves are moving this way, but at a frequency of 0.10 hertz, but yet she accounts the wavefront at a higher frequency. This means that she's actually moving against the beach. She's moving against the waves in order to account it at a higher frequency. Therefore, she's actually moving this way, away from the beach. So we can get rid of option A and option C. So we're left with option B and D. Now, what we can do, we can actually find the speed of the wave. The speed at which she is going. Because we have the frequency, we know that the speed is 0.4. And to find the wavelength, we can, because we're meant to multiply by wavelength, we can use our information up here. So the wavelength of these beach fronts is just 2 times wavelength, and the wavelength is 20 meters. So we can put that in here, and 20 times 0.4, 20 times 0.4 is 8. So we're moving 8 meters per second this way. But this being said, the beach is actually pushing her this way by 2 meters per second. So we have to take 8 minus 2, which gives us 6. So the answer for question 29 is B. Now for question 30. We know that the gravitational potential is V at distance r above the surface of a spherical planet with radius r and uniform density. Now the gravitational potential at distance 2r would be what? So I'm just going to draw a quick diagram of the planet. And we know that this is r, and we are right here. And at this point, the gravitational potential is V. Now we have to find out what the gravitational potential if the distance is 2r above the planet. So now we can find the formula, which is Vg for gravitational potential is the gravitational constant multiplied by the mass over radius. So initially we have this is not radius, this is the distance from the center of the mass. So initially V, as you can see here, is equal to minus gm, and the distance is 2r. 2r because we have from the center of the planet, so we have r and r. We're looking, r in this case is the distance from the center of the mass, whereas r here is referring to the radius. So this is our first equation. And now what happens if we make the distance 2r above the surface of the planet? What we get is we get Vg is equal to 3R. So as you can see, we have increased it to 3R. Now what this means is that we actually are dividing this more by 3. Whereas in this, V is equal to this. So how do we manipulate the terms here? Well, what we can do is, as you can see, V times 2 would make it equal to minus GM. But we're looking for a 3R underneath here, which means we have to divide by 3. So V2 divided by 3 is minus GM over 3R, which works out to be our answer, which is option D. Okay, so for question 31, we have a force acting between 2 point charges is F when the separation between the charges is X. And now this separation is increased to 3x and we're asked to find the force. So this is another one of those comparing questions. And what we can do is we can use the formula that tells us the force between two charges. You can find this formula in your data booklet, section 5.1, where we have force is equal to Q1, which is charge 1, times Q2 times K over R squared. So initially we have a force of F, and we have R as X. So we'll just have it like this. And now this is increased to 3x, so we have force nu, and this becomes 9x because we have to square the entire term, so including the 3, which gets us 9x squared. So if you compare the two terms, what's different about it is that we have actually included this 9 now on the term. These is the exact same. So new force is basically just the old force divided by 9. And that gives us answer of C. Now going on to question 32. Imagine that you have a uniform electric field and an electron enters it with a velocity v. As it gets deeper into the electric field, the field strength will increase. Hence, the path will actually not be circular, but actually parabolic. So the answer for question 32 is B. Now over to question 33. Now this is a bit of a hard question. It's actually a Lenz's law question. So we have a current going downwards like this. And now we can actually use our hand to figure out which way does the magnetic field is induced due to this direct current going through coil Y. So if you use the coil rule, as you can see, our thumb is pointing this way. So magnetic field is going this way. So I'm just going to draw a few lines here. So what this means is that we actually have a south and a north around here. That's how I would imagine it. And now we have the plate X. X is moving towards it and away. And we have to determine what current, whether the current direction is the same as Y or not. So if we move X towards Y, we're actually passing through this magnetic field. And what Lenz's law said is that as there's a change in magnetic field, that induces a current. And the current direction will be whatever direction that opposes that change. So in this case, the change is because we're passing through a magnetic field that is pointed this way. And Lenz's law tells us that the induced current has to induce a magnetic field that way. So if we use our hand to kind of figure out what way it is actually downwards as we move away from Y. And that means that we can eliminate option A's and B. And now, if we move away, what we're getting less magnetic field this way, which means that we're actually going to induce a current that increases magnetic field that way, which means the direction of the current would be the same in X. Hence, the answer is C. Let's move on to question 34. So in question 34, we're presented with 4 options of a graph. We have the magnetic flux and the EMF. So magnetic flux is actually what induces an EMF. So the change in magnetic flux induces an EMF. So the correct graph is when EMF, when the change in magnetic flux, EMF is equal to 0. So when there's no change in magnetic flux, EMF is equal to 0. So as we can see here, there's no change in magnetic flux at these areas because it's going up. This is 0 and it goes back down. 0, 0. And when magnetic flux is 0, so is the EMF. So that means that for question 34, the answer is B. So going on to question 35 now. Question 35 is a capacitance question. So let's just go to our formula booklet, subtopic 11.3, which is capacitance. What we find is that we have a formula for capacitance that is capacitance is equal to the charge over voltage. So now we're asked to find the current. So we know that V equals IR. We have the resistance, so we have to find the voltage. We can do that by using this formula. So we know capacitance is 1 UF, and I'm going to leave everything the same here because the units here are the same. So we have 1 equals charge 15 over V, which means voltage is 15 UF. So voltage is 15 UF, and we have a resistor of 25 ohms, which means current is 15 divided by 25, which works out to be 0.6 if I'm correct. Yep, 0.6. Now, what we have here is that now we have to decide whether to choose option A or option C. Now, if you did your units correct, it should work out to be option C. Now moving on to question 36, this is a diode question. Basically what this diode bridge circuit does is that it forces the AC current into just DC, into the resistor. So we can play a different scenario here. Let's assume that we're half a cycle in and the current is coming this way. So what this diode does is that it forces the current to go through here. It forces it to go through Q. And vice versa, assume that we're half a cycle later and we reach here. It forces the current to go through Q, pass through the resistor, and come back through S. So let's go through each point. When diode P conducts, Q does not. So for diode P to conduct, that means that Q has already come in. And now we're going outwards like this, because the charge has already used up its energy into the resistor. So as it passes through P, Q does not conduct. Now when diode S conducts, neither P nor R conducts, and that is true too, because it comes in and now it's heading back to point N. Now let's look at 3. The direction of conventional current in the resistor is from left to right. Now this actually differs because we don't like the circuit here does it changes between AC because it's alternating. So we're not too sure about point 3, hence the answer is A for question 36. Okay, so question 37. An electron of low energy is enclosed within a high potential barrier. What is the process by which the electron can escape? So straight off by reading that, you should already know the answer for this, and it's A. It's called quantum tunneling. It's when electrons with low energy can jump through barriers of potential. Okay, next question 38. We have a beam of radiation of photons, made out of photons, with momentum p. Now the intensity of the beam is doubled without changing the frequency. So what we can look here is actually, if we go to subtopic topic 12, we see that the energy in radiation, E, is not dependent on the intensity. It's actually depending on frequency. And the frequency does not change in this case. And, oh, sorry about that. We know momentum is made out of mass and velocity. So if the energy doesn't change, that means it's not gaining any kinetic energy either. Hence, momentum should stay constant, and that means our answer for 38 is just P, option B. Now we're on to question 39. We have to choose which observations are evidence that an electron behaves as a particle. So electrons' emissions as a result of the photoelectric effect. So we know that that is correct. Electron diffraction, as an electron interacts with an atom, we know that's false. And we know that this is correct too. Which means for question 39 is option B. Now moving, last but not least, we have question 40. So in question 40, what we have here is we have a sample of radioactive nuclide containing NO atoms at time equals 0. Now we're asked that time t, there are n number of nuclide remaining in the sample, and we're given the half-life to be t and subscript half. And we're asked, what is the decay rate of this sample proportionate to? So we know in order for a nuclide to decay, it needs to have existing number of atoms remaining in order to decay. The less amount you have remaining, the less activity you get, the less decay you get, because there's less amount of atoms that could potentially decay. That means for question 40, our answer is actually n, and this is because the decay rate is proportional to how much atoms we have left that could be decayed. And I hope that makes sense.